everyone. I am Eric Williams, and I want to welcome you to our Parking Structure and Durability Educational Webinar Series, proudly hosted by the Concrete Preservation Alliance. Over this four-part series, industry experts are guiding us through, participants through conversations about inspection and assessment, post-tension system protection, targeted corrosion mitigation design, and long-term global protection planning to ultimately provide a practical framework for durable parking structure solutions. Today's session is titled Tailored Protection, Designing Targeted Corrosion Mitigation Solutions for Parking Structures. In this session, we will move beyond a one-size-fits-all approach to highlight how engineers and owners can design targeted mitigation plans based on their structure's needs. If you are new to the Concrete Preservation Alliance, welcome. We're a coalition dedicated to promoting best practices in concrete repair and preservation. Our mission is to offer free, accessible, and non-commercialized education, sharing practical knowledge from professionals in the field to support long-term durability and sustainable infrastructure. We extend our sincere thank you to all of our members and supporters worldwide, whose collaboration and dedication make the Concrete Preservation Alliance and educational events like this one possible. If you missed any of our past sessions or want to rewatch or learn a little bit more, you can always catch the replays of this session and the ones, like I mentioned, from the past on our website, wesavestructures.info. And before we begin, one of the best parts of our seminar series is audience participation. So please don't hold back. If you have any questions throughout the webinar here, that you post them in the chat. We will be giving away a $100 Amazon gift card to the person who submits the best question. Speaking of speakers, let's meet today's presenter, who is Nick Drews. Nick is a business development manager in the US and takes care of the Midwest for Vector Corrosion Technologies. He attended the University of Winnipeg and University of Minnesota, where he built a strong materials science background while obtaining his chemistry and then his chemical engineering degree. Nick spent the last 15 years growing his career at Vector, where he's worked extensively in research and development, and as well as the business development team here in the US. So thank you, Nick, for joining us today, and I'll throw it to you.
Perfect. Thanks, Eric. Thank you for the introduction. Good afternoon to, I think, most of you. Good morning to some, I suppose. Good evening to others. Here's the outline of the presentation I'm going to cover. I'll start with some corrosion background review, get into patch repair risks, move on to design considerations, and then finally, with that background built up, we can get into some of the corrosion mitigation solutions. With this corrosion background and review, session one did a very good job at covering this in depth. So I'll give a bit of an abridged version, but I need to maybe level set some language for those who didn't attend session one, so we can give the rest of the presentation so it all makes sense. So if you've heard a presentation from me or seen a presentation from me, I like to start with this question. Being in the industry and the role that I'm in, I get asked a lot, why are anodes used in concrete? Now, anode is a term that we kind of just expect people to know, but what does that even mean? I think we need to ask a different question first, maybe something a little simpler. So what is corrosion? So typically, when people think of corrosion, they think of the red rust. So the red rust is the anode part of the reaction. That's only half of what goes on in corrosion. So the anode is where electrons are lost and oxidation occurs. And in the case of steel, you're going to have section loss as well as expansion from the corrosion products. Okay. Now those electrons lost from the anode don't just go nowhere. They do go somewhere. They travel along metallic path to an area called the cathode, or the non-corroding part of the metal. Okay. That's where, again, electrons are accepted and no oxidation takes place. So for all intents and purposes, you have two electrodes: corroding metal, non-corroding metal. Corroding metal is the anode, non-corroding metal is the cathode. Okay. And that is the exact same science as a battery. And that's how I like to think about galvanic anode systems, is they are quite literally batteries that are consumed over time, and we can choose which of those metals is the one that corrodes. One last thing on this slide I just wanted to point out is you can see corrosion isn't exclusive only to certain elements. wherever you have steel reinforcing embedded inside of concrete, there is some risk of corrosion, and I'll talk about what affects that risk as we go forward here. So I mentioned session 1. So Pratik Verkute back on November 5th, he gave a very good corrosion background review. I encourage you to go watch that if you want a more in-depth corrosion background. He did a very good job, but I will give you an abridged one here moving forward. So I think it's helpful to look at the background of the component products we're talking about. So looking at concrete, it's a hard sponge. It's porous. It allows liquids and gases to move in and out of its structure. Great in compression, poor in tension, which is why we have reinforcement in those areas that may see tensile forces. And it's naturally highly alkaline. And that alkalinity is a good thing in terms of steel reinforcing, but I'll tell you why in a couple slides. The other component product here is steel. So like session 1, I like to think of corrosion in terms of energy. Coming from an engineering background, it's where I feel comfortable thinking about it, and intuitively it makes sense to me. So iron ore comes out of the ground, it's mined, very, very low energy, very stable, but it's useless for construction purposes. So to get it into anything worthwhile, we have to put in energy. We heat it, we shape it, we change the oxidation state, we roll it, we make it a highly ordered system, and we get something like a piece of rebar. That highly ordered piece of metal, it doesn't like to stay that way. It wants to give the energy that you put into it, it wants to give it back to the environment where it came from. So that's all corrosion is. It's giving that energy back to the environment that it came from. And if you look at the far left here, a piece of iron ore, and the far right, this fully corroded bar, they look very, very similar, and that's because they are very, very similar. Again, Pratik from session 1 talked about this cycle of energetics. That's what we're seeing here. It really is a cycle of introducing energy and it just wanting to give the energy back. So this corrosion of rebar, of embedded steel, it's inevitable. Eventually it will happen, but you can do things to slow it down. And I'll talk about a few of those going forward. So the corrosion of the bar itself isn't necessarily the issue. It's more that when steel corrodes, it expands and it puts tensile forces inside of this concrete that we know doesn't like it. And that's when you see the cracking and spalling. Corrosion, it can affect both conventionally reinforced as well as pre-stressed or post-tension elements. So with conventional reinforcing, usually you're going to see these signs of concrete cracking and spalling well before you have a structural issue. So you can go ahead and fix it before it's a problem. On the other hand, with pre-stressed or post-tension elements, you may lose structural capacity kind of well before you get those physical signs of concrete cracking and spalling. Not the presentation for it, but session 2 covered pre-stressing and post-tensioning quite thoroughly. I encourage you to go check that one out. So you might be asking yourself, why on earth would you put this piece of reinforcing that wants to corrode, and when it corrodes, it expands into concrete, which cannot take that expansion, okay? Fortunately, good quality concrete has a high pH, and it creates an environment that helps steel hold its energy. It's that high pH. I'm not going to get deep into the chemistry here, but just know it creates something called a passivation layer. It's like a little cocoon that keeps the energy in the steel and stops it from corroding. Very, very durable combination, steel and concrete. And that's why it's very widely used in construction. So the problems really take place when you have that passivation layer break down. Now I have this flow chart. It comes from a document from the TRB, Transportation Research Board. It's called the Sharp 2 project. It refers to bridges specifically about getting their design life to 100 years plus, repairs to 100 years plus. The concepts from the corrosion section, which is very thorough, they apply to all structures, including parking ramps and parking garages. So that's why I included it here. The causes of corrosion of steel and concrete: chlorides, carbonation, dissimilar metals. So chlorides, they could be either cast in, maybe you have an accelerant, maybe you have an aggregate that's chloride contaminated, and corrosion can initiate, break down the passivation layer. The other way, and probably more likely for me in the Midwest, de-icing salts applied to the surface throughout the winter, things melt, and then that melt off, just leaches through the porous nature of concrete, reaches the level of steel at a certain level, and corrosion can initiate. Now, if you're on the coast, that could be a marine environment. Saltwater is the same thing. Continual exposure to a marine environment can also build up chloride levels and break down the passivation layer. The next one here, carbonation. Carbon dioxide and carbon monoxide, just from the atmosphere, over time, will leach through that concrete, react with the free lime, and the free lime is what gives the alkalinity. So by reducing that, alkalinity is also reduced, and corrosion can initiate due to that. And in some cases, both of these, chlorides and carbonation, will be an underlying cause for corrosion. This is typically found in older structures, carbonation, or those with low concrete cover. But just know, both are causes. And dissimilar metals, that's actually the concept we're going to use for sacrificial galvanic anodes. When you couple two different metals fundamentally together, you have a metallic path and an electrolyte path to complete a circuit. One of those two metals will act as anode and corrode, and the other one will act as cathode and be protected. And again, we can use that knowledge to our advantage to protect the structures in consideration. Final thing, again, from session one, I'll give credit to the speaker there. You need moisture. So follow the water. On your structure, if your drainage is done very, very well and things are well taken care of and you have very good maintenance practices, you can keep corrosion from initiating from a very long time. But if you do have drainage issues and water continues to go over certain areas, you're going to get continual exposure of things like chlorides. And that's typically where you're going to find your issues. So that's a key one. Used to have a colleague working in Arizona. We used to joke, the corrosion capital of the world. Very little moisture, very little corrosion. So that is a key consideration as well. That's my abridged background on corrosion. Again, I encourage you to go to session one if you want to learn more. Now I'm going to move on to some risks of patch repair. And again, I need to recall from session one, there is a non-destructive test method, or rightly maybe a semi-destructive test method called the half-cell potential survey. It gives you the probability of active corrosion in a structure without having to physically see it. So you need to take a multimeter or a voltmeter, attach one lead to the steel and question of your structure, the other lead to a reference electrode, and you can read off a value. And the values can tell you the probability of active corrosion going on. So with a copper-copper sulfate half cell, any number more negative than minus 350 indicates you're in an area of active corrosion. Probabilistically, anything more positive than minus 200 indicates you're very, very likely in an area of passivity. This is a very powerful technique to give you a picture of what's going on in your structure. So I showed you that to show you this. And this particular diagram may be something people have seen before, but I do want to touch on it because I think it's important to get to the point that I'm talking about. So what this is, for those who don't know, it is a concrete slab with two layers of reinforcing, one on the top, one on the bottom. You have chloride exposure from the top. That is the dotted lines here. You have some equations over on the left. I'm not going to get deep into what that is really saying, but it's chloride reacting with iron and turning it to iron oxide. One thing I do want to note is the chloride ion is both a reactant and a product. So once you have that contamination inside the pores of your concrete and it reaches the level of steel, it doesn't go anywhere. It has to be addressed in one way or another. Just wanted to put that out there because that is quite important. The other thing you can see on the right here, this little hatched out X'd area, that's the passivation layer that's been broken down on the top bar. You can see on the bottom bar, it's still intact. And then if you were to do a half-cell potential survey of the top and bottom layer, you're going to get these two numbers. An area actively corroding, minus 350 or more negative, and an area that's passive, minus 200, or more positive. And if you look at the corrosion activity, it would corrode to the most negative area. The driving potential, the difference between two of these, is what really causes this corrosion. Now, you don't necessarily need this second bar in this completely passive area to cause corrosion. You can have areas on the same bar that just have a higher chloride exposure. So in this case, you can see this area has a higher chloride exposure than the one adjacent to it. While both are showing signs that they're in an area that is more than probably actively corroding, only the most negative or hazardous area is the one that actually corrodes. It's going to be the most electronegative. Okay, everything in its area of influence is actually going to be protected. So this will act as anode. These two areas will act as cathode and not corrode. So what does that look like? All the corrosion activity goes towards that minus 500, the most negative number. So I want to bring you back to the Sharp 2 research project and move you along to options for currently corroding structures. The first option, we always have to point out, is to do nothing. You can do nothing as an owner or an engineer and just monitor the situation. It's going to give you, the lowest life extension, but it will be the cheapest, at least in the short term. It is always an option. And what does that look like in this case? If we just did nothing, the corrosion activity would just continue to go to this minus 500, the most negative area, most corrosive area. You're going to get corrosion, expansion, concrete cracking, and spalling. Okay, so usually this is the physical sign indicating to an owner, hey, I need to get this repair. Now, options for currently corroding structures, again, you could do some sort of treatment perhaps to reduce the rate of deterioration. That could include maybe a waterproofing, maybe some sort of corrosion inhibitive admixture. For this case, it may be a little too late. Even if you had an admixture in a repair, that's going to protect inside of the repair, which is not necessarily what we're concerned with. We're going to be concerned about the area around the repair, and you'll see why. The other option, partial removal and replacement. Perhaps we can remove all of the chloride contaminated concrete and replace it with nice, fresh, healthy, high pH concrete. And that in itself should do the job. But as you'll see in this case, not always practical. Maybe the element is just too big, hard to get to, hard to replace. So in this case, with just a regular patch repair, right here, you've chipped back until you found sound concrete, you cleaned up the bar as best you could, but you can see what's left. Chloride contaminated concrete immediately adjacent to your repair. So the unintended consequence from repairing this damaged concrete without understanding or addressing the underlying corrosion is patch accelerated corrosion. All that happens is the corrosion activity flips to the area adjacent to your repair. You get corrosion and you get cracking and spalling. And it's patch accelerated because you don't have the same time lag of needing the chlorides to diffuse through the porous nature of the concrete. It's already there, so you don't get potentially decades of time lag like you with a new structure. And again, session 1, Pratik referred to this. Here's an example he showed where they did a half cell potential survey, and this owner did a patch repair while not addressing the area adjacent. And the area adjacent, you can see there's a lot of hot spots for corrosion, and I would expect that potentially they may have to come back in the next few years and repair that once it's corroded. So if we can't just remove and replace, because we're at risk of patch accelerated corrosion, what are the other options? So cathodic protection is one, electrochemical treatment is another. I'm not going to touch on electrochemical treatment. We have some other presentations for that on the We Save Structures website. I encourage you to go look. But that refers to chloride extraction or realkalization. Very powerful techniques. Maybe it's right for your structure, but I'm not going to discuss that here. I encourage you to take a look on the website. But I am going to discuss cathodic protection, and specifically galvanic. So cathodic protection, I defined it up front. That's trying to make the steel the cathode part of the corrosion reaction, the non-corroding electrode, by making something else the anode. And galvanic, that basically means it's natural. We're using a dissimilar metal that's going to have a natural electrochemical difference that will cause this galvanic corrosion cell. And what does that look like? And it looks like this. Zinc, you can see this is a galvanic series of elements on the right. Everything further to the right is going to be more corrosive. Everything further to the left is going to be more noble or non-corrosive, passive. So zinc being further to the right than low alloy steel, and you can see this number is much more negative, minus 1100. Everything in its area of influence is going to be protected or cathodic, non-corroding. The only thing that corrodes is the zinc. Okay, and when zinc corrodes, fortunately for us, it doesn't cause the same expansive forces as the steel would when it corrodes. A lot of this zinc corrosion product will be accepted into the porous matrix of this galvanic anode itself. So that was some patch repair risks, and I'm going to move on now to some design considerations. And I want to take you back to the concrete preservation process. This was touched on in session 2. Before we even get to developing a repair strategy, we need to go through these other steps. Otherwise, we're just kind of taking a shot in the dark, hoping our repair holds up. First thing you're typically going to do is you got to identify the issues, right? Could be cracks, spalls, delaminations. You have a corrosive environment, some pretty clear water leakage. Maybe these other things are also affecting your structure as well. Once you've identified some issues, you do evaluation. And again, speaker from session 1 talked about a lot of these, non-destructive testing as well as destructive testing techniques. The one I touched on that's very important in terms of characterizing corrosion are corrosion potentials. Once you've done this evaluation and you've identified the issues, you can take all of this data, take a look at it, analyze it, and determine your underlying cause. So one of the key things with any kind of repair, you got to ask yourself, what caused the deterioration? So that's what the evaluation and issue identifying hopefully helps you with. And in the cases I'm going to talk about, it's corrosion, but it could be a number of things. It could be multiple things. It could be, corrosion and freeze thaw, and poor drainage and carbonation. It could be a number of things, but determining the cause is very important because if you don't address that, your repair may not stick like you'd like. And then moving along, you got to ask yourself, are repairs required? If the answer is no, okay, continue with maintaining and monitoring as usual. But if the answer is yes, then we develop a repair strategy. And from a corrosion perspective, we know a lot more than we ever did a couple decades ago. We can be very precise with the protection provided. So there is some industry guidance out there from AMP, the Association for Materials Protection and Performance. This is a NACE standard, National Association of Corrosion Engineers. It used to be a standalone organization, but now it's under the umbrella of AMP, as well as coatings professionals. This standard, SP0216, had an update in 2023. You can read it right off here. Refers to galvanic cathodic protection of reinforcing steel in atmospherically exposed concrete structures. Exactly what we want to talk about. And what that latest update really stressed was that designers of galvanic cathodic protection systems need to consider the performance of anodes over their design service life, because we know so much more than we did, even 10 years ago, 20 years ago especially. We know anodes degrade predictably. They exponentially decay, and over time, they are giving off less current. It's never just going to be horizontal, get the same current the entire time. It's just never going to happen with a galvanic system. And the reason this current goes down, a number of reasons, but one of the main ones, zinc is consumed over time. So remember, it's like a battery. It is a consumable, but also there are other things at play, and I'll talk about those. But resistance building up in the circuit, polarization of the steel and the zinc, those also come into play for this current degradation. So one of the fun things about math, about the nerdiest thing you'll hear me say, if you have an exponential decay curve and you put it into a logarithmic plot, it becomes a straight line. And with anodes specifically, you can see how the slope is different. So this graph is published in a research study that Dave Whitmore and George Sergey gave and presented in 2021, research study on the aging of anodes and their performance over time. If you want to know more, I encourage you to go read it. Reach out. We can send that your way. These three degradation curves, aging slope curves on the current dropping, it's on the same structure, using the same types of anodes, just at different spacings, different things going on. And I want to show you this to tell you that we know which knobs to turn to make this aging curve either very flat or very steep. We know what changes that slope. And here are the essentials for design, which I'm going to touch on one at a time in the examples. So corrosion risk, steel density, temperature, and the internal chemistry. Some will just call it simply zinc activation method. Yes, that is a big part of it, but there is a little more to it than that. And for what that's worth here, this is from 25 years of results from the very first anode install, the Leicester trial. Very cool project, still monitored to this day. Now, moving on to the solutions. Finally, we're here to talk about parking garages in need of repair. And I just do want to give a disclaimer on this. So my goal is to get the basics across. I'm going to simplify some things. You know, I'm not trying to teach a PhD. I'm not doing a NACE CP3, NACE CP4 class for corrosion design. But I do believe that a large part of science and engineering is understanding the trends, which knobs you can turn to get things to move the direction you want. And that's hopefully what I can get across to you. So the first example I want to talk about is a Kansas City-based parking garage. It's cast in place. It was experiencing concrete deterioration that was corrosion driven. And we needed to determine the best way to target the underlying cause and ensure the repairs don't fail early. Ultimately, we're trying to put the owner's money to the most effective use. You can see in the pictures on the left, you can have the anodes installed at the perimeter or on a grid to prevent the halo effect as necessary. So the halo effect is going to work in 3 dimensions, depending on where the exposure is of chloride and your steel layout. So you may need to put them on a grid, and in some cases, on the perimeter may work just fine as well. In this case, utilizing galvanic anodes in the repair, it allows us to leave chloride-contaminated concrete, corrosion-driving concrete in place. Can limit repair areas, save time, save money. And I just wanted to show you that these little green halos around the point anodes, that's the area of influence of each one. We want those little areas of influence to overlap so you have a blanket coverage just inside the edge of the parent concrete. Now, these are the questions we need to ask ourselves in the middle. What is the project objective? And for design, what's your corrosion risk? What's your steel density? What's your temperature? And then what's the internal anode chemistry that affects the current decline? So first question, what is the project objective? Okay, easy, quick discussion. Owner wants corrosion to be mitigated for 20 years. So that's what we're designing for, with the end of life in mind. Corrosion risk. So there's an ISO standard that says corrosion prevention or cathodic prevention ranges the amount of current density from 0.2 milliamps per square meter to 2 milliamps per square meter. That's quite the range. That's a 10x range. So hopefully I showed this earlier in the presentation. When you have areas that are more chloride contaminated, the corrosion risk increases, and the number you actually see on a half cell goes up as well. So as the chloride level increases, your risk of corrosion actually increases as well, and the amount of current density you need to arrest corrosion follows the same trend. So higher chloride level, more current is required. And there's actually 3 levels that we as Vector have found that are sufficient through our 20 plus years of research and field trials. The minimum amount you're going to want if you're in a low to moderate risk, which is less than 0.8% by weight of cement, is 0.4 milliamps per square meter. Then you have a high range, 0.8 to 1.5%, 0.8 milliamps per square meter. And then you have an extremely high range, Anything above 1.5%, 1.6 milliamps per square meter. And where can you find these numbers? Well, typically you're going to need to take a powder sample or take a core, send it to a lab, get it tested, find out what the chloride level is at your level of rebar. Because everything above isn't going to affect the rebar. But what it is at the level of rebar, that's what we care about. And if for whatever reason you can't, take powder sample or get a core, we as designers would try and use structures that are similar to the one in question in the same area, perhaps seeing similar exposures, and we'd use a conservative estimate to fit into one of these categories because we're trying to design specifically and tailor specifically for the structure in question. So in this case, the corrosion risk was high, so we know what we need to aim for. 0.8 milliamps per square meter at year 20. Because once our current level drops below this 0.8 number, corrosion can reinitiate. Even though we're providing current, corrosion can reinitiate based on chloride level. The next thing, steel density. You can see here it's a ratio, the surface area of steel divided by the surface area of concrete. So I'm not here to do a math class. I'm not going to do this calculation for you. If you want to know more about it, send me an email, send a question, and I can get some resources for you. But just know it's simple math. Because the thing that actually corrodes in the structure is not the steel core, it's only the surface area that interacts with the concrete. So that's what we're trying to protect, the amount of steel surface area. We want to protect that with zinc surface area. And there needs to be a proportional amount to get the life we're looking for. So to figure out the steel density overall, you're taking every bar, every piece of exposed steel that you can, longitudinal, transverse, both directions. If there's 2 layers, you take both, add them all up, do the proper calculation. In this case, the steel density was 0.98. Okay. The next thing, temperature. Temperature matters because every 18 degrees Fahrenheit or 10 degrees Celsius increase doubles the rate of corrosion and makes the anode life essentially in half. Fortunately for us, so Vector has spacing charts on the website and on our technical data sheets. I can't speak for other anode manufacturers, but on those spacing charts, they are designed for the average annual temperature in the Midwest. So around 50 degrees Fahrenheit, Kansas City, it's pretty much right there, so we don't have to worry about doing that adjustment. But if we were working with some of the senior designers back at main office, they're probably using special spreadsheets and design tools that wouldn't be on the technical data sheets, and they'd be able to account for this. I want to refer to the technical data sheets specifically because they're available to the public. They're on our website, for consumption. Anyone can use them. So like I mentioned, that's something to consider. Every 18 degrees. So I will say there is a caveat to this in the Midwest. If you're in a structure that's like a boiler room, a steam tunnel, that may be at an elevated temperature just annually. So that would have to consider this this temperature increase. But in this case, we're outside, we're in a parking structure, don't need to worry about it. Now, here's the 2 spacing charts I talked about. This is on the technical data sheet. We have ones for a 10-year design as well as a 20-year design, depending on what you're trying to do. We've determined in this case, we're looking for a 20-year design. Okay. We are in the high corrosion risk, so we have to choose that off the chart. And then within this high corrosion risk, we know what our steel density is. It's 0.98, so it falls into this category. So for a 20-year design life, you can use this XPT or smallest galvanic anode every 8 inches on center, the medium size XP2 every 13 inches on center, or this largest XP4 at 17 inches on center. And in every case, you can expect a 20-year design life. It's nice to have this flexibility in design because as an owner or a designer, to make it easy for the contractor actually installing these galvanic anodes, you try and pick the number that's closest to a multiple of your steel, of your rebar. So if you have rebar every 8 inches on center, then you can just say, hey, let's put an XPT every 8 inches on center. Or Maybe you don't want to install them every bar. Well, let's put an XB4 every 8-inch or every other bar, 16 inches on center. Just makes it easier for you on the install side. And these numbers, this is a maximum spacing for 20 years. So if you went a little bit tighter, you would actually get a little bit of a longer life because the anodes would be worked a little less hard. So the battery would be able to be extended a bit. Okay, so this is the expectation. With this type of design, and we know Vector's internal anode chemistry, the aging term is about 13 years. So every 13 years, the current is in half. Now we can use that knowledge to work our way backward. So at year 20, we want to be at 0.8. Then at year 7, we should expect to be at 1.6. And then at initiation, we should expect to be around 2.2 milliamps per square meter. So you can check this. These systems can be monitored. I encourage you to do it if you're curious and you want to make sure you're validating what you're getting. This is the expectation: 2.2 milliamps per square meter, and a decline over time to reach this design goal of 0.8 milliamps per square meter at 20 years. Okay. Now, the last consideration I need to cover is the internal anode chemistry differences. So this information is widely coming from this research study that Dave Whitmore and George Sergey gave, and I'm not going to get too deep into it, not my place necessarily. I would encourage you to read it if you want to know more, but this range of anodes can give us some flexibility in design, okay? But if you did a design using a vector GalvaShield, which again, I can only speak for vector GalvaShield, in the example used in this research paper, they had roughly a 30-year design life. They were aiming for 0.4 milliamps per square meter. You know, they worked their way back to time zero, and you're at about 2 milliamps per square meter. So what George and Dave did is they looked at published data from an alternative type of anode out there, saw how the aging was looking, and if you were to design for the same initial current, because the aging term was so much steeper than the vector GalvaShield, you just dropped below the usable current pretty quickly in comparison. And if you were to look at, you know, the example that I used for this Kansas City garage, the same sort of thing, you know, instead of getting around, let's call it 16 years, it's much less. And the reasons for the internal anode chemistry differences, I mean, it's how zinc is utilized. It's the efficiency, resistance buildup from corrosion products. There's more to it than just throwing a hunk of zinc inside your structure and hoping that you get protection. There are things that need to make sure it works. I'm not saying one is better or worse. They are just different. So you can't take a vector GalvaShield design, just take a completely different type of anode using a different type of chemistry and expect them to work the same. You just won't get what you think you're going to get. Every anode manufacturer should be able to tell you what to expect in terms of current decline. So if you're using a product, I encourage you to ask about it, ask for that information just to make sure that you're covered and you're getting what you're asking for. Again, not saying one is better or worse, but they are just fundamentally different from a chemical point of view. Moving on. Now I'm going to move on to the Dundas Street garage here in Toronto. The reason I wanted to show this is because in their repair, they use some epoxy-coated bar. And it's not that the epoxy is the big deal here. The epoxy, fundamentally what it does is it reduces the amount of steel that needs to be protected. You still need to make your electrical connection. So you can see here, they stripped away some of the epoxy, tied up the anode. And you can check this electrical connection by using a multimeter. You know, you touch one end of your multimeter to this anode wire, touch the other end to the steel you're trying to protect. And if you get a number less than 1 millivolt DC or less than 1 ohm DC, you can be pretty sure that you are connected. Yeah, I wanted to show this example because they used a very similar project objective, 20 years. The corrosion risk, essentially the same, being in Toronto, but the steel density was lower. So I want to see how it affects our curve. Temperature, same-ish, and the internal chemistry is the same. It also used one of the vector GalvaShield anodes. So looking back at this chart, what happens to the curve? Well, it gets shallower. The trend is a slower degradation of current and a shallower aging slope. All other things being equal, the half-life increases. So what do we have? The same starting point, but it's a shallower degradation, and you actually could get a longer life because the steel density is lower. Now, you could look at year 7, this current's higher. Year 20, the current's higher. The aging term is higher. If you want it to be economical as an owner, instead of spacing the anodes as per this line, you could just space them a little wider because there's less steel to protect, and you could move that aging curve back to where it initially was and get your 20-year design life. So that's how the steel density would affect this calculation. Next thing I want to talk about, Ship's Tavern Garage in Wilmington, Delaware. This was a situation where they used drilled-in targeted protection. So something unique about this structure is that it has, some welded wire rebar on top. We have some studs connecting it to a galvanized pan decking. So this galvanized pan decking provided structural capacity, and you can see there's corrosion activity going on the bottom, which is not good, especially if it's providing structural support. And think about the amount of corrosion activity going on to eat through the galvanizing and then also show signs on the bottom of the structure. So VCS durability was brought out due to a half cell potential survey, found that there was pretty widespread corrosion activity going on in this garage, and something needed to be done. But one thing to note is that the concrete's actually in relatively good shape, but because of the way the steel pan decking is, a lot of the water and moisture kind of making its way through cracks and through pores, it just kind of sits on it and is essentially eating away at the structural pan deck. So looking at our options for currently corroding structures, the thought was, can we use cathodic protection, specifically a galvanic option? So that would be the CC. This is a cylindrical type of anode. It is fundamentally the same as the XP style, except it's meant to be cored into a hole. You have zinc surrounded by an activating mortar. That's the anode chemistry. And then you make a connection to the steel, whether through a rivet or maybe a drill and tap. You have a lead sinker connection, all of those things. Any one of them is possible, but you just need to make sure that it's done. One of the caveats here is that there was very high steel density. I mentioned it. This pan decking is connected to everything electrically. So the trend is a much faster degradation of current and a steeper aging slope. All other things being equal, the half-life really decreases in this case. So going through this design process, they wanted 20 plus years. Corrosion risk was high. Steel density, very high, especially that pan decking in there. Temperature, same-ish as the other two. Internal chemistry was the same. It makes this aging term much, much smaller. And the slope, as a result, is much, much steeper, and you're getting a much shorter life than you want to have. So it would be difficult to fit a proportional amount of zinc into the structure and still achieve that life extension goal, just because of the amount of steel. We need to fit a proportional amount of zinc. Really, really tough to do in this case. So what else could they do? So they looked at this other option, uses a fusion two-stage anode, where it has an impressed current piece. In this case, it's a fancy way of saying a battery, where a higher current is pushed out initially to passivate this currently corroding steel. And then once that higher current is depleted, the battery is depleted, it will naturally switch over to this galvanic piece, the zinc, and the maintenance requirements of current are much, much lower for something that has been passivated. The analogy here you can think of is friction, static friction versus kinetic friction. It's harder to get something moving than it is to keep it moving. So once you have it moving, it's easier to keep it there. Once you have something passive, it's easier to keep it there. So this is a vector alkaline fusion anode. The aging term is going to be increased compared to that pure galvanic option. And this is sort of what that aging curve looks like. Phase 1, a higher current output. And then once that's depleted, you get the galvanic piece at a much shallower angle, and you're going to get a much longer life than just purely galvanic. One other cool thing about this structure and the way they did this repair is they were able to use some, somewhat limited dollars to the best of their ability. So VCS durability was brought out to help with the actual layout of the anodes. They went and did a more in-depth half cell survey and found the most corrosive areas and really hatched out and put little dots where they needed the protection. And I believe the installer here was Vector Construction, as well as Pullman was on site there as well. So just know, putting all of these concepts together, you can get a really tailored solution and a targeted solution to the areas that really, really need it. And you can see what we've done here. It's a more shallow aging curve. Next example, Roosevelt Garage in Lansing, Michigan. This was a garage that had precast double T's that were degrading right at kind of the ends, because you had water ingress leaking into these slots where the strands are. With this one, got to ask again, going through the process, what's the project objective? The answer, 20 years, 20 plus years. Corrosion risk, high. It's roughly the same as the other options, other examples, sorry. Steel density, it's actually much lower than the other ones. You can see there's only like 6 strands. You take those into account. And then there's a couple of stirrups and vertical bars here. But overall, steel density was lower. Temperature, same-ish as the other ones. The internal chemistry, it's the same. Vector Galvus shield alkaline. One of the considerations here is that there's insufficient space to fit an embedded anode. Because even if you did want to fully open this area up, you're going to release all the tension from the strands, and then they're not doing you too much good. So they want to keep all of that in place, but there's not enough room to fit an embedded anode because this is such a small profile, this precast double T stem. So what could they do? And I've alluded to it, a surface applied approach. So the contractor went ahead and repaired the areas that needed it. And in the repair, while it was open, they made their electrical connection. They, touched all the wires, made it a durable connection, ran that lead wire out, and then they could come afterwards, do some surface prep, install this surface-mounted DAS anode, and this is kind of what the final product looks like. You have this socket protecting that lead wire. It runs up into this little conduit area built into the anode, and this will actually be protected as it's run over to the end, and there's end caps to make sure it's not a weak point. It's actually going to be a durable solution. So very cool idea here. You don't need to have embedded anodes for protection. You can also have a surface applied approach, but it needs to be thought out. And what does that thinking look like? Okay, steel density, they determined to be roughly 0.6. This degradation table was actually taken from one of the spreadsheets I had a designer send to me back at home office, and I wanted to show what this curve looks like. And this is what it ends up being. At the spacing that we decided, which was basically 1 per stem end, we end up getting roughly a 30-year design life. And if you work your way back with a 13-year aging curve, we're starting roughly at about a 0.63 milliamp per square meter, which totally fine. Oh, sorry, this is per square foot. It'd be a 6.3 per square meter, factor of 10. And this is what that anode looks like. Same sort of concept as the CC and XP type. You have a zinc core in a highly alkaline activating mortar, and then all of this extra stuff here is to mount it onto the wall and make it proper for the structure that is going on. Last example I want to show, an Omaha-based parking garage. I'm not going to go through this design. It was the exact same as the Lansing design. But instead of protecting these precast double T stems at the end, they were able to protect midspan. So I just wanted to show this to show that you can really, really target this protection where it needs to be, where the actual degradation is, where perhaps you have drainage issues. One thing I want to note here is these lead wires were saw cut, or they were put in conduit afterward to make sure they were protected. Because if they're left exposed, it's a potential weak point. So we want to make sure we beef up our potential weak point and actually make it into a strong point. So another thing here, the key, don't always have to embed the anode. You can protect from the surface as well. Finally, I'm at the summary slide. I know many of you are probably have heard enough of my talking. So here we are. This is more words than I'd normally put on a slide, but this allows you to go back afterwards and read this through, and then you don't have to hear me speak. But I will go through this one point at a time. Corrosion in structures is the same science as a battery. Hopefully I've shown that. In a cathodic protection system, we can choose the metal that degrades, aka we can choose the anode, we can choose the cathode. The halo effect can be mitigated with a properly designed galvanic cathodic protection system. Again, hopefully I've shown you that. The design of a galvanic cathodic protection system should not be a guess. We know so much more about the science and what goes into design. You do not need to guess. You really, really shouldn't guess. Choose your desired life extension, design for it. The current output of galvanic cathodic protection systems decreases over time. Again, it's not going to be a constant current. It's impossible. Fact of life, you're going to have a degradation over time. This one, very important. Key considerations in the design that affect performance. Your corrosion risk, your steel density, the temperature, and the internal anode chemistry. All very, very important to consider. Last thing, cathodic protection anodes can be embedded and or surface applied. So with that, I will pass it back over to Eric for some questions.
Thanks, Nick. Really, really nice job. A lot of great information in there and a lot of really good questions came through. So I'll start rapid firing some of these and see what you think. Okay. So the first one, and you touched on it a little bit, it's in regards to weather, fluctuation and environments and how we take those into account. So are there any special considerations to take into account in construction or repair parkades in high fluctuation weather environments such as Canada? You know, they have very cold winters, of course, and their summers do get pretty warm as well. So what are your thoughts on that?
Right. Okay. So you're right. I did touch on it a little bit. So what we look at for the design is the average annual temperature. So what's going to happen is the corrosion activity will go up in the summer and it'll go down in the winter because heat is energy and energy adds to the corrosion activity. So that's taken into account. Average annual, that's what we're really looking at.
Right. Something else that comes up quite a bit is the maintenance and monitoring. I know we talked a little bit and we'll learn a lot more about global and possibly active systems in the next webinar series. But for targeted cathodic protection systems, what level of long-term monitoring and maintenance is required from the owner to ensure the system remains 100% effective over the 20-year service life or whatever the design life might be, whether it's 15 or 30 years?
Okay. So a big part of that, so you can do two things. You can direct connect the anodes and set it and forget it, and you shouldn't have to worry about corrosion activity. The way to make sure that it's done well is you're going to do a QA/QC check. I touched on it a little bit. You take a multimeter and you check for electrical continuity. You're going to do that with both the steel you're trying to protect, touch adjacent bars with your multimeter, make sure that number is less than 1 millivolt DC or less than 1 ohm DC, and you can say they're electrically connected. And then when you install your anode, you'll do the same thing. You're going to take your lead wire from the anode and the steel you're trying to protect. Make sure that number is less than 1 millivolt DC or less than 1 ohm DC. That would be the direct connect option. And all of that insurance is going to be done up front. Now, if you were doing a monitoring system, instead of directly connecting, you would isolate the anode, that lead wire, from the steel. You'd run it out of the concrete into a monitoring box. And in that monitoring box, you would run it across a shunt of a known resistance, and you can measure the voltage across that shunt. You're going to run the other side of the shunt back to the steel, probably through a switch where you can turn it off and on. And since you have two values, the resistance, because you know what that is from the manufacturer, and you're measuring the voltage, the third thing, using Ohm's law, if you remember your high school chemistry, you can measure the current. You can measure the current passed over time. The other thing you can do is have an embedded reference cell. So I touched on polarization of steel. There is a criteria of a polarization, means you're shifting its corrosion potential, essentially. I'm not going to get deep into it, but you want to shift the corrosion potential into an area that's more passive. to reach a cathodic protection level that's defined as 100 millivolt shift. You can use this this half cell permanently embedded in your structure near the steel, and you can measure kind of the corrosion activity of your steel. And if you have a switch inside your monitoring box, you can flip it on, turn it off, and see how things are reacting. There are other presentations that get deep into the monitoring. I encourage you to go watch those, but that's in general how it works. You have some different things you can play around with. Some stuff you have to make sure you do up front, but really powerful, pretty reliable stuff.
No, that explained that pretty well. And I know there's a lot of projects out there that with galvanics that some are and some are monitored and they like that, and some are, and a lot are not. So it's really up to the owner and the engineer what they want to do, which is pretty much right on there, Nick. So thank you. Here's one. This is a good one, and I don't know if it's been asked on a lot of the other webinar series and things that we've done. And I'd be interested to get your spot on this one, Nick. Is does placing the anodes around the perimeter of the repair reduce or displace the halo effect? And while helpful in the immediate area around the repair, if the concrete outside of that range of the anodes is also contaminated, could an acceleration of the corrosion be observed at that distance from the repair instead of right besides the repair? So from this question, I'm kind of gathering, is the risk of using an anode just pushing that halo effect further away where the anode's not affected?
So the answer is, I'm going to kind of punt on this a little bit. I'm going to say it's kind of, okay? So when you fix the most corrosive area and you get rid of that, really, really negative corrosion potential, very, very active area, if you don't do something to address the area immediately adjacent to it, it will corrode next, no doubt. And one of our previous presenters, George Sergey, the first person to do an anode project in concrete, he said it well. If you don't do something to cathodically protect, you force anodic destruction. So the area beside will corrode. Now your anodes placed at the perimeter, that will protect that, the halo effect, okay? Areas outside of that's not going to be halo effect driven. That just might be some other corrosion activity. So there have been cases where there have been half cells done to the areas throughout the garage that have indicated, here's areas of active corrosion, but they haven't cracked and spalled the concrete yet. Here's an area that needs repair. So in the area that needs repair, XP anodes were installed around the perimeter, and then these other areas that have shown that have shown to be actively corroding but haven't cracked and spalled the concrete yet. At the same time, while the garage was under construction, they drilled in CC type anodes to get ahead of that, because that is very likely going to corrode at some point in the future. But since there was all this disruption with the repair project in the first place, you can couple those two together and make a pretty durable fix so you don't have to come back any sooner than you like. So hopefully I answered that sufficiently.
Yeah, no, very, very interesting on that one. So thank you. Another one that came in is the slab depth play a role in determining what type of anode we use, whether it's an XPT or a 2, because of how much room you have and the limitations on site.
Yeah, no, it definitely can. That's one of the reasons we use that surface mounted anode on the precast double T's, because there's not enough room to embed an anode. I usually say, like in most cases, if you're doing an open repair and you can fit an anode in, it's probably easier than coming back and putting something surface applied later. But back to your main question, yeah, we designed these anodes to be kind of as thin as possible to fit into these smaller areas. So we have a minimum of 1 inch of concrete cover is what we like to see. Anything less than that, you could perhaps experience some sort of reflective cracking, and you don't really want that. So you want to make sure you get that 1 inch of cover at a minimum. And if at all possible, you could install it on the side or underside of the steel. That's a good option. There is one particular type of anode. I didn't talk about it. So the XPT, we actually have a smaller one. It's called the XP Compact. It's made for tiny little repairs in facades. The whole point is we want to make it easy for contractors to do the installs. So limit the headache, make them as small as possible, but it definitely plays a role. If you can't fit an XB4, then you can maybe have to go with something smaller like an XBT and just use more of them.
Excellent. The surface mounted anodes. Does that allow these surface mounted anodes to be replaced after their lifeline if the life extended after installation? So essentially, is it feasible to replace the surface mounted anodes, once their service life has been depleted?
Yeah, absolutely. That actually is one of the unique things about the surface mounted. Actually, another unique thing about the surface mounted is that you could theoretically put in a monitoring system after the fact, because you can interrupt the line that directly connects it to the steel. But yeah, to answer your main question, once the usable life of that surface mounted is up, say it's 20, 30 years, whatever it may be, yeah, you can pop it off, put up a new one, and you can actually reuse those electrical connections. You may want to do some checks, of course, always QA, QC to make sure it's working properly, but yeah, absolutely.
Are there any differences in determining the number of anodes for, say, a concrete pier repair compared to a concrete deck repair? What are the inputs that you would need to say, okay, we're going to use this in this situation and this in this situation?
I mean, realistically, you're going to ask yourself all of those same questions. What is the project objective? And then you're going to determine what is the corrosion risk. I suspect in a pier situation, it's going to be sitting in perhaps salt water as opposed to a deck situation where it's not going to see the constant splash. That pier situation, it's probably going to be a higher corrosion risk. Steel density, I would bet you the pier's also got much more steel in it. So that's going to take into account. In terms of temperature, if you're in the same bridge, it may not be a difference there. Anode chemistry, if you're going to use the vector alkaline, it's going to have the same activation type. But with a pier situation, there are fixes. So we do something called a galvanic encasement, where if you have chloride contaminated concrete, behind bars, under stress, you may not want to chip all that out. You can leave that in place, and we would do something, called an encasement. You're going to have an overlay of some galvanic anodes. You're going to determine the exact spacing based on those questions that I talked about the entire presentation, and you can just do a slight overbuild and do the protection that way. But the actual design in itself, there may be some slight subtleties to it, but you're asking yourself the same questions.
No, good point at the end there, Nick, because another question came in regards to, have we done this on concrete foundation wall repairs or for vertical wall concrete repairs as opposed to suspended concrete slabs? And I think the answer to that would be yes, and you just mentioned it there. And then also for larger scale repairs, make sure that shameless plug here, tune in for our seminar in February that will go over more global protection systems, which I think that would be absolutely a part of that. In terms of questions, how about we wrap it up with this one? Is there any recommendations on the properties of the repair material that you're putting back? And is there an effectiveness or a performance, or when we're using a repair material, what is it that you look for, Nick, and say, okay, this one would work or be compatible with the anodes?
Okay. Yeah, Bill, that's kind of an easy answer. The material that you're repairing with and you're embedding the anodes in has to be less than 50,000 ohm centimeters of bulk saturated resistivity. That number actually used to be lower, but there was a white paper and a research study done. Again, I love seeing things done through research and development. 50,000 ohm centimeters. As long as you're less than that in terms of resistivity, you should be good to go. And if you do have a situation where your repair material is more resistive than that, there's a way to work with that. You'll have to pack the anodes in a conductive ionic bridge. We have embedding mortar for that actually has extra activator in it to help the anode work. But you'd have to pack the anode kind of like a little bridge to the base concrete, so you can send the current where it needs to be. Because remember, we're not necessarily trying to protect inside the repair. That's getting a fresh concrete mix. That should be corrosion inhibitive already with its high pH. We really want to protect the parent concrete left in place. So 50,000 ohm centimeter, that's the number you're looking for. If you ever have a question as to whether something meets that, you can always send it our way. The other thing you might see is rapid chloride permeability, a number greater than 500, and you're good to go.
Excellent. Well, I think we'll wrap it there with questions. Nick, really appreciate you and your time and all the education that you shared today. We'll wrap things up. If anyone has any other questions or would like to reach out to Nick directly, his contact information is provided, so please feel free to do so. If there was a question that was not answered, Nick will be reaching out to you individually to make sure that your question does get answered, and we can touch base on that. So if you wanted to review any portions of the presentation again or share it with others, we'll be posting it to our YouTube channel tomorrow. As I mentioned earlier, all of our previous webinars are posted there as well for those who may be looking to look more. And as I mentioned at the top, this is the third part of our 4-part series on parking structure durability. Our last session will be on February 15th, where Matt Miltenberger will be exploring global corrosion mitigation solutions for parking structures. So if you enjoyed this session and are looking for more information like this, you can scan the QR code on the screen. And if you miss it here, no worries. You can always go to our website, wesavestructures.info/webinars to register now. And while you're at our We Save Structures website, you can check out our environmental impact calculator. That is a free tool that helps you estimate the environmental benefits of repairing versus replacing concrete structures. What we've gone ahead and used the calculator to estimate the emissions that would be negated by repairing one of the structures that Nick referenced earlier. It's the Ship's Tavern parking garage that's located in Wilmington, Delaware. If this were to be rebuilt instead of preserved, it would have needed approximately 4,100 cubic meters of concrete. By entering that in at the top there, you can see what the waste and emissions would be created and how much natural resources would be required to rebuild this garage. I think one of the most impactful examples is the amount of energy that's used in cement production would be the equivalent energy needed to boil 15 Olympic-sized swimming pools. So you're keeping quite a bit of tonnage of CO2 and emissions and everything out of our landfills, quite impactful, and that's a free tool for anyone to use as they see fit. That'll do it. So thank you everyone for attending. We know everybody is busy out there. Again, big thank you to Nick for all the work and all the education he passed along today. And hopefully we'll see everybody in our final installation of our parking garage durability seminar series, or webinar series, excuse me, next in February. So in the meantime, hope everyone has a good rest of their day and go out there and save some structures. Thank you.